The answer is no. Okay, ladies and gentlemen, welcome back again. For those of you who don't know me, my name is Joris Melkert, and I'll be your host in this lecture room today. I'm going to listen to these three presenters who are going to talk about their design project. They've been given 20 to 25 minutes for their presentation, then there's 10 to 15 minutes for questions, and after that, 4 of them will already receive their bachelor diploma, and we give the honors to do that to the coaching team. But that's for later. We first want to give them the floor. We also have the possibility to follow this via live stream, so that's why we have the second microphone. Now I'm going to give that to the presenters as well. You need to hand it over from one to the next, of course. You can clip it here or something like that. But that also has a consequence for the questions. The questions come from the audience. Please repeat the question before answering it, so also the people at home can follow what's going on. That said, I'm going to give this to the first presenter. And I'm going to dim the lights a little bit. And then the floor is yours.
See if this works. Yeah. Thank you, Joris, and welcome everyone to the symposium presentation of Group 11's project Vortex, in which we design an unmanned aerial vehicle for the internal inspection of wind turbine nacelle. I am Sebastian Wagner, and I am the project manager of this wonderful group of 10 aerospace engineering students who have been able to call my colleagues for the past 10 weeks. As you can see, we've both been assigned an engineering and a managerial role for this project. Well, look through it quickly because I'm going on. Today, we would like to tell you what we did the last 10 weeks. And we'll do that with the use and the help of a visualization of a general inspection routine for the drone. First of all, let's start off at the docking station and talk about what we're going to talk about today. I will start off the presentation with the problem statement. So, why is this project needed? After which, I will give you the mission objective, so the what and the how, and also some requirements and constraints on the project. Marcus will follow up with the system engineering and subsystem design of our drone, of our project, and lastly, Eva will round off with the final design and some sustainability remarks. So, first of all, as promised, let's zoom out a little bit and look at why is this project needed, the problem statement. Like any mechanical system, wind turbines need frequent inspections. This is to either, well, get rid of failures that reduce the efficiency of the system, or detect failures earlier on so they don't result in major breakdowns. And currently how that is done is by technicians. The technician has to go in person to the wind turbine and see for himself whether something is wrong, and if something is wrong, what's wrong. This introduces some high costs and also some risks for the technician. First of all, let's look into the costs. There's some big numbers on the screen, but what it comes down to basically is that the two major players in the driving costs are comprised of the vessels that bring the technicians from shore to the offshore wind turbines, and on the other hand, some lost revenues, so indirect costs. This is due to the fact that the wind turbine can't operate whenever a technician is present, due to safety reasons. Reducing these numbers is quite straightforward. Well, the idea is quite straightforward. We want to reduce the amount of times a technician has to go offshore, so no lost revenues and also no boat trips. Second to that, there's also the safety issues. Whenever a technician has to go offshore, he has to travel sometimes 100 kilometers over rough seas. When he gets to the wind turbine, he has to enter confined spaces, he has to handle equipment there, and well, all the while being 100 meters up in the air. This introduces some risks, as you can imagine. Once again, the solution is rather straightforward. The implementation maybe not, but we want to reduce the amount of times a technician has to go offshore. Well, but the whole sector wants. So, now that we know why we are needed, let's zoom back into the nacelle and see how currently this is being dealt with. Because, as I said, we're not the first ones to think about this. And this also follows upon our mission objective. So, currently there's two major players in how they're trying to reduce technician inspections already. SCADA and CMS. They're basically gathering many different operational variables of the wind turbine and basing models on those, and those models can predict how a wind turbine should behave. If the actual behavior of the wind turbine deviates from this, this may indicate a failure. That's the basic idea behind it. Now, unfortunately, those models aren't perfect, so that's where we come in. We can now, combining all this, state our what and how our mission objective. So what do we want to do? We want to improve the current condition monitoring systems to reduce the amount of time the technician has to go offshore. and thus reduce the induced cost and safety issues. How we're going to do that, however, is with a UAV to, well, complement on those condition monitoring systems. Not replace them, but complement on them. Now that we know how and what we have to do, let's look at some requirements and constraints, some challenges for us. So, as soon as we move off the docking station, the first challenges already emerge in the form of, for example, a GNSS denied environment. GNSS denied basically means there's no access to GPS or any outside help for navigation. So the drone should be able to navigate and position itself on its own with the use of solely its sensors, well, and as I said, no outside help. This is being more challenging since we're in a confined space. As you can imagine, a wind turbine nacelle isn't a very, well, spacious environment, so we have to watch out that we don't deviate from our path too much and, well, crash into anything. Another challenge is the fact that it's a high humidity environment, since we're at sea. And lastly, there's also the very diverse nacelle architecture. So the architecture changed from wind turbine type to wind turbine type. This means that for our design, we have to be very flexible in this, because we want to be able to fit in every single nacelle. The biggest split in the market is almost a 50-50 split. On the left side, there's geared wind turbines, which, as the name suggests, includes a gearbox between the rotor and the generator. And on the right-hand side, a direct drive. So there's no gearbox, and the generator is directly linked to the rotor. When looking closer into the direct drive wind turbine, you can see that here the generator is the dark gray structure. And when the drone is placed in the back part of the nacelle, we won't be able to really see anything that happens in front of the generator, nor on the side of the generator. So this gives us very limited information about whatever is going on with the nacelle and also its health. So it was quickly decided that we will not be looking into this, unfortunately. We will leave it for future research, but we will solely focus on the gearbox type wind turbine. Some further requirements that were put on our project by either us or stakeholders is that we have to include at least a visual inspection camera and an infrared inspection camera, along with an additional non-contact sensor for the inspection of the drivetrain. There's also the need for a 25-minute minimum inspection flight time, which is, well, challenging since we have confined spaces, so small drone. Small drone means small battery, well, challenging for 25 minutes. Next to that, there's also the need for residency, so the drone has to be able to operate on its own in the wind turbine without any help from outside. So no regular inspections by technicians, it has to be able to charge itself on its own, and so on and so on. And lastly, there's also a safety requirement. Since we are operating in a very, well, high-cost environment, we don't want to crash into anything in the first place, of course, but especially not in this high-cost environment. We have put some strict safety requirements on the drone. For example, if subsystem fails, like a rotor, we want to be able to, that the drone survives, be able to still fly and land safely either on the ground or back at the docking station. Now that we know what and how we want to do and what some requirements on the system are, we have to combine this all into one project that complies with all of this. And I would like to hand the word to Marcos, who is going to further explain this to you.
Hi, good morning. My name is Marcos, and I'm the systems engineer of Project Vortex. And I will take you through the entire process of designing a complete drone to solve this challenge, these ideas that we have already proposed. Well, let's start. Let's go through the nacelle and start with the systems engineer section. So this is a three-step process. We start with some preliminary concepts, some ideas, some possible solutions to solve this issue. Then we follow with some sizing. How much should the drone weigh? How much power should it consume? And we last finish with some subsystem level design. Let's start then. So, from preliminary design, we selected three possible concepts, three possible solutions. We start with a pusher concept, a puller concept, and a coaxial concept. Pusher and puller are fairly similar, but coaxial has a quite big difference. While they all have the same amount of rotors, coaxial has two rotors, one on top of each other, thereby the name of coaxial. And this gives the advantage of being able to use larger rotors, which is very nice when one of your limitations is the size of your drone. However, there's also an issue with it. as the top propeller spins, it generates some aerodynamic interference with the bottom one. This is called aerodynamic wake, and it reduces the efficiency of the drone. However, we have realized that for our application, coaxial still yields many benefits. In addition to this, we also selected a payload, which is mainly composed of 3 sensors: a thermal sensor, a visual sensor, and an acoustic sensor. Moreover, for reliability purposes, we decided to go with octocopter, meaning 8 rotors, 8 motors, and 8 power units. And lastly, we also selected a communications, a control system. So I would like to say, for example, for the control system, it's established in a two-loop cascaded style. So we start with an MPC constraint handler, and we finish with an PMPI attitude controller. For communications, we use Wi-Fi 6. So we start communicating from the drone to a docking station using this method, and then the docking station communicates to ground using the already existing infrastructure. Okay, now we know possible solutions. Let's move on to some sizing. So we established this sizing tool, this optimizer, based on the 3 main driving subsystems behind the mass and power consumption: propulsion, power, and airframe. We started with an initial guess, some guess that it was mainly based on literature of 3.22 kilos, and we finished with a final maximum takeoff mass of 3.92 kilos. Additionally, for hovering space, our estimated power consumption is around 1600 watts. Now, knowing this, we are going to move on to subsystem level design. So we finish with system engineering, and we drive through the nacelle into the next step. All right, let's begin. So, payload. As I said a second ago, our payload is mainly established by three sensors: an infrared sensor, an RGB sensor, and an acoustic sensor. However, fortunately, there's a lot of cases in which the infrared sensor and the RGB sensor are put together. Therefore, we have decided to also just focus on looking for components that already bring this together. It helps with reliability, it helps with ease of use, etc. And we found out this nice company called Volkswagen and this specific camera, the Iris Pro, which is specifically designed to be used on UAVs. And additionally, we also selected a group of two microphones in the audible range to detect issues such as gear meshing, etc., etc. Now, as a summary of payload, we are capable of seeing thermal differences of up to 30 millikelvins. We hear in the audible range, so 10 to around 20 kilohertz, and our visual spatial resolution is 0.04 millimeters at minimum, which is nice and is advantageous for things such as surface crack detection or just general visualization of the nacelle. Additionally, we also designed a communications data handling human interaction subsystem. This is mainly based on Wi-Fi 6 and is capable of delivering up to 36 gigabytes, which are generated from the payload sensing. Moreover, guidance, navigation, and control is one of our most important subsystems. This is the subsystem that is going to move the drone around and is going to decide the path, etc. Therefore, we decided to really focus on robustness on this. And we are proud to say that we have been able to achieve 8 out of 8 scenarios where the drone remains stable after 1 engine inoperative, and 24 out of 28 scenarios where 2 engines inoperative means the drone still flies. Propulsion has also been designed with the same thought process in mind. As such, even though our nominal consumption per rotor is around 113 watts, we are capable of delivering 360 watts per rotor or up to 90 newtons, which means around 2.3 Gs. And additionally, electrical power system works similarly. This means that we have designed it with a battery of around 240 watt hours that yields 7 minutes sorties. Our interest is to focus on somewhere around 25 minutes inspections. Therefore, we have mounted the power subsystem with a battery exchange mechanism, which allows us to quickly exchange batteries so that operators or autonomous missions don't take too long via recharging. And lastly, we're very proud to say that we designed the airframe subsystem using finite element analysis, and we have been able to reduce the weight of this subsystem to 200 grams. 200 grams over a drone that is 4 kilos is an amazing achievement. We have also used this finite element analysis method to test for all the possible scenarios that we could think of in which the drone might break, the airframe might break, and none of these scenarios mean catastrophic failure of the subsystem. Now, knowing all of this, I'm going to pass the microphone to my colleague Eva, who's going to give you a summary of the entire product and how it behaves.
Thank you, Marcus. Oh, yes. Cannot forget about the people back home. Do you want to do it? Okay. Thank you. Thank you, Marcus. Hi, I'm Eva Rodrigues. I'm the Risk Manager and Propulsion and Power Chief of Group Vortex, and I am here to present you our final configuration. Well, after 10 weeks of hard work, we came to this final beautiful drone, an octocopter with a coaxial configuration, which means we have 4 pairs of rotors, one on top of each other. And as you can see on top, we have the lidar for navigation, which is complemented by a rangefinder, which is on the bottom. On the bottom, we also have our payload, which is a 2-in-1 visual and infrared camera with the microphones on each side. This came up to, as Marcus already said, a whopping 3.9 kilograms. This is amazing for such a range endurance drone that we have. And a maximum dimension of 50 centimeters, which is approximately the size of an adult male. And as they fit inside of the drivetrain comfortably, so will our drone. But what is a drone without a mission, right? We need to look into that a bit more closely. Our operations are split into 3 main parts. The ground station, where the operators are closely monitoring a fleet of drones through an amazing user interface. The autonomous mission, where our drone will, on its own, fly around the drivetrain and collect data on the different components and possible faults. And the manual mission, on where, if SCADA or our drone detects a fault in the drivetrain, the operators on the mainland can remotely control the drone to go closer to the drivetrain and further inspect this fault. Looking closer to our autonomous mission, it is split into 3 main parts. The drone starts at the docking station, in blue, and it then performs 4 sorties. Between each, it returns to the docking station to swap batteries. The first 3 sorties, it collects infrared and visual data on the gearbox, main bearings, and generator. And then, on our final sortie, it collects acoustic data. But you wonder, acoustic data, won't our propellers interfere with the measurements, right? For this, we're going to perform perching, which I will tell you a bit more about in a minute. This accounts to a total inspection time of 22 minutes and a total mission time of 45 minutes. Now, on to perching. This was one of our main challenges, as not all nacelles are different, the inside is never the same, so we can't come up with a single solution for everything. So we proposed 3 solutions. The best one would be for the drone to land on the ground, if there's available space, as no extra infrastructure would be required. But this is not always possible, as it can be a very cluttered space. So our second solution would be a wall attachment. We have a platform that can be flipped up and down when there's on-site maintenance for people to still pass. But sometimes there are electrical cabinets on the walls, and there's no space for this platform. So our last but least appealing solution would be a platform that comes from the ceiling down and can be pushed up again for humans to pass more easily. Now, we've looked a bit of our final product. We are very happy with it. We're going to go back, and after all of this, we are producing a product for wind turbine farms, right? They're all about sustainability and the environment and clean energy. So we don't want our product to hinder this goal. Thus, we had to make an analysis on how sustainable our product actually is. For this, we looked at environmental, financial, and social sustainability. Starting with the environmental sustainability, we did a full life cycle analysis of our drone, from manufacturing, production, operations, to even end-of-life disposal. And we came to the conclusion that our drone emits, for a fleet of drones that is on a 30 gigawatt wind farm for 30 years, every year each drone emits 53 megakilograms of CO2. You might be wondering, wow, this is a lot. But the same wind farm, just from the vessels that go there for on-site inspections, every year emits 26 gigakilograms of CO2. This is just the vessels, mind you. So we would offer a reduction of 500 CO2 footprint at the end. Not only do the vessels emit a lot of CO2, but also every time someone is in there to inspect the drivetrain, they have to shut down the wind turbine. This means that we have loss of green energy. In fact, 13.7 megawatts hours every year per wind turbine is lost due to maintenance and inspections. With our drone, you don't need to have downtime. And our drone only consumes 148 kilowatt hours per year for powering the batteries. This means that without having downtime for inspections, we could power per wind turbine 5.2 more houses in the Netherlands with green energy every year. I know everyone likes environmental sustainability, but we also looked at our financial sustainability, and wind turbines are a growing sector, and so is the demand on maintenance. And with all the problems I have already stated with the current inspection procedures occurring, our product will have higher demand as the years are coming. Not only that, but we also made a high effort on selecting products that are mainly manufactured in Europe, or at least we took into account the geopolitical situation of nowadays when selecting our products. Finally, our social sustainability. My colleague Sebastian has already told you that it's a very dangerous job to be working at such high altitudes. They're just hanging by some threads. This is extremely dangerous. So if we are reducing the amount of time they are up there performing inspections, we are promoting a safer work environment. Not only that, but less vessels going there for inspections means cleaner oceans and cleaner air for the communities living close to the shore. We do have one downside. We will be eliminating some inspection jobs for offshore inspection, but this can be easily fixed by repurposing these workers, by teaching them how to work with our drones and the user interface to be then working onshore, monitoring our fleet. Well, as you can see, we did a great work. I'm very proud of what our group accomplished. And we started with one challenge, to reduce offshore wind turbine inspection, on-site inspection. And we came up with a great solution, a resident UAV that complements the current monitoring conditioning and offers the possibility to take a closer look at the problems that are current on the drivetrain. And instead of people having to go there to see how the problem is, they can already come with a solution. Thank you. We are Group Vortex, and we thank you for your attention.
Lovely, thank you very much. I'll give you a little bit more light, so you're literally in the spotlight. Then I'm going to see who's going to ask the first question, and then I'll give the microphone to you to divide the questions over the best answer. Yes, Vince.
Thank you very much for the presentation. Why is it better to have a UAV than just fixing video cameras to the wall?
I think I can answer that question on my own already. This question has arisen a couple of times already before. To have the same, well, first of all, the problem with fixed cameras is, of course, that either you have one camera that's fixed to one place and you can't move it around, so there's a lot of, well, dark spots, for example, behind corners or whatever. And if you want to get rid of those, you would have to include many, many different cameras, right? Well, our drone only needs, one camera for the whole drivetrain. So that would reduce the amount of costs and also, well, installation complexity and whatnot, other kind of challenges.
Did you make a market study of what is available today?
A market study, yes.
What is the competitive advantage towards the solutions that are already in the market?
Please repeat the question.
Oh yeah, sorry. So if I repeat the question, if we did a market study, to which the answer was yes, and then did we look into competitive UAV solutions?
What is the competitive advantage of your solution as regards the solutions that are already in the market?
So what's our competitive, solution to options that are already in the market? Okay, then Selim, please answer.
Well, currently there is no any UAV or any other company that is targeting the drivetrain specifically. There are other drones for the other parts of the wind turbine, such as the blades, and there are other types of drones that need piloted flight for confined spaces. However, there is no company that tries to do it autonomously, which is our biggest pro compared to other companies. So we have a clear market space that we can fill. Does that answer your question?
Thank you. So if we could give a little bit more clarification on the trade-offs in... Okay. Marcos?
Yeah. So we performed our design process was split into two stops. Firstly, is what we call the midterm, and in this one we did all of the preliminary design. So all of the choices that I presented at the beginning, and our main system level choice was the coaxial or flat pusher puller design, and our basis was to make sure our trade-off was mainly based on the confined space, so trying to fit within the nacelle, which is we have considered to be not a extremely big space, and weight. We determined weight as one of our bigger driving factors, not because it's extremely important, as for us the drone should just be able to carry the payload, but weight is our way of sort of understanding the feasibility of this design. After using weight, knowing that the weight should be below around 4 kilos, lets us select these sort of drones that are already feasible. We validated this selection with this external tool that I quickly went over, and we came to the conclusion that many times the weight being around above 4 kilos meant that the drone was unfeasible for factors that were not accounted for during our design. Say, for example, overheating. If the drone was above 4.5 kilos, the motors would be mostly capable of delivering this thrust, but they would be running at a very high power, therefore overheating and most likely causing failure. Does that answer your question, or?
In your drone configuration, you mentioned that the flight time is very dependent on the weight, the payload of your drone. And therefore, you now have to exchange batteries, I think 4 times during one inspection. Have you considered also reducing your payload by, for example, also swapping your sensors, that not carrying all of your payload all the time? And would that have been perhaps an improvement, or perhaps splitting your sensors over 2 separate smaller drones? Have you considered different configurations for the system?
So to repeat the question, if we have considered different configurations regarding, well, maybe instead of swapping a battery, swapping either sensor load you take with you, or yeah. Any takers?
Hi. We didn't per se consider different configurations, which is a very fair point, but also our microphones weigh 10 grams, 3 grams, they weigh nothing. So the advantage would be just not having the camera, I guess, which is the heaviest component. But we are performing most of our missions with the camera at the end of the day, and even adding up the 3 sorties we have with the camera, it wouldn't be feasible to have such a small drone to perform just in one go. So the battery swap was the most possible solution. Does this answer your question?
Next question.
Yeah, I was wondering if your drone adds another layer to what is already existing. There is already existing sensors. How many interventions do you save, or amount of observations, human observations do you save by applying your system?
So question, narrow down, how many observations do we save with our drone? Oh, have I again? That's good.
This is really hard to quantify. We tried, but there are industry secrets to get this data from the O&Ms on how often they actually go there, just for maintenance, just for inspections. It's hard to specify, but currently they schedule every year, twice a year missions to perform inspections and maintenance. But for example, if they spend, these are 2-week-long missions. If they spent a whole week on just inspections and then they have to wait for components to arrive for fixing and maintenance, we could already reduce the time they're there and making the risks shorter.
Can I add on?
Yeah, you can add on.
There's also, whenever failure is spotted by either SCADA or CMS, then we offer the solution is that how it's done today, since they're still, well, in development sometimes, CMS, for example, for specifically. There's still a high false alarm rate in those, and whenever a failure is spotted by any of those systems, then there still has technician, still has to go to the wind turbine and see if the failure is really there or not. And then our UAV can provide that second opinion, so we, well, also save that trip. Does that answer the question? Thank you.
I think we have time for 1 or 2 more questions. Anyone would like to challenge
Simple.
this? Yes, please.
I would like to ask about the maintenance of the drones itself. Has it been accounted for? How expensive it would be? How the time of working will require to keep them safe? Thank you very much.
Thank you for the question. So the question is, have we accounted for the maintenance of the drone itself? Okay. It's our very greedy take.
I performed the REMS analysis on this. That's why I'm so excited. But hard work. Our maintenance our components that require the most maintenance are the payload sensors, which require calibrating every year. So once a year, they do have to go to the wind turbine to calibrate our sensors. Other than that, scheduled maintenance is for the batteries, which the worst case scenario, every 3 years they need to be replaced. But this is accounting that only we lose 90% of capacity. So this is, we could extend it. And they are closely monitored, so perhaps 4 years, 5 years even. And then we have unpredicted maintenance, which is only scheduled to happen after the end of life of the drone from our calculations. So we are safe on that department. Does that answer your question? Yeah.
Let's do 1 more question.
The environment inside this pod, is that an important environment? Because there could be a lot of heat generated, and is that taken into account in your design of your...
That's a very fair question. Thank you for the question. So the question was, does the environment influence our drone in any way? For example, temperature. Oh, it's funny because yesterday, or are there any other? Yesterday we went to the drivetrain to look at one that's on the ground to training pod, and we experienced that it was very warm in there, even though it was inside what's it called, a hangar. So yeah, very fair question. And yes, our drone does take this into account. For example, the thermal sensors, they have an operating range until 60 or 70 degrees or something like that. So we've done some, well, very preliminary literature research because it's very hard to get this information about the drivetrains and their operating temperatures. And well, our drone and its sensors fit well in between, within that range. So, does it answer the question?
Okay, thank you very much. Give them a big hand again. Okay, thank you very much for answering those questions. Now it's time for the tutor team to address the team and also hand out 4 diplomas. And this is going to be indeed a team effort. The principal tutor, Donatella, and one of the coaches, Josephine, will make this a duo job, I think. Please use both microphones. You can hold them in one hand.
Yeah, okay. Ooh. Okay, good morning, everyone. I'm Donatella. I was the tutor of Group 11. And Josephine is here with me. She is the coach, together with Anton, who unfortunately is not here. He's in Sweden now for the summer school. So, first of all, I would like to say that it was a pleasure to tutor and being with Group 11 for 10 weeks. It has been a very hard work for them. The topics, were a little bit complicated because they were combining drone knowledge with wind turbine knowledge that they didn't have from the bachelor. So I really acknowledge this. It was a big effort. It took some time as a team to get together, but eventually I'm very proud to say that they got together and then they worked very well together. And this is a big achievement that I would say, because this is a lesson that you will learn for your life as well. You will be always working in a way or another in a team, and then learning how to deal with others is the most important thing to me. And I really want to acknowledge this. You did a very good job. And then, yes, well done to all of you. Yes, all of them have done a good job. There are the project manager. I would like to acknowledge Sebastian did a very good job to keep the group together. Eva, what is Eva? I can't see. Oh yeah, Eva is sitting there. Marcos, Maino, Selim, Kira, Julia, Seb, Dennis, and Akil. All of them, very, very nice job. And then I really liked the idea of working with them, seeing them thinking about how to solve this problem, which was a little bit difficult at the beginning. And then they managed to fix it. They are super smart engineers. And then, yes, I'm very proud of what they did. So do you want to say something, Josephine, on top of this? Yes?
Yeah, just to add on top of what Donatella just said, I'm very proud of what you achieved. It's, for me, also very cool to see what a group of 10 students can come up with, because I've been in your seats myself. And you did an amazing job. And similar to Donatella, I want to acknowledge you really came together. You delivered a nice product. Thank you very much.
Okay, thank you very much. Now it's time for 4 students to get the diploma as graduated bachelor engineers now. How we're going to do this? I'm going to call the name, then you come forward, and I guess the 2 of you will give the diploma. If there's people in the audience who want to take pictures, please come forward. We have plenty of time for doing that. You can step down here. And the first diploma is from Mahino Bertrand Marc Assi. Anyone taking pictures? Yes, you can come down if you want. Just take your time. You have to keep smiling, huh? Yeah, and I'm also going to give a folder to you to store it in. The next one is Eva Garcia Rodriguez. Eva. And smile for all the pictures. I see at least a dozen cameras. See several people struggling with cameras, but because there are 2 people still struggling with cameras. Yeah. No, okay. Okay. Okay, and also for you a folder to store it safely. The next one, Selim Kazanci. Anyone taking pictures? There's someone taking a picture, or maybe a colleague of you? I can take it. Oh, thank you. Okay, because this is a once-in-a-lifetime opportunity. It's free. It's free. And then the last one is for the team leader, Sebastian Wagner.
Yes, Sebastian.
And I'll give you a folder as well, of course. This is yours.
with one camera.
Anyhow. Okay, and also have a folder for you. Thank you very much. Please take your seat again. Because then I'm going to close off this session. Congratulations to all the young engineers receiving their diploma. I assume the others are close to that as well. With your diploma, be extremely careful. There's only going to be one bachelor diploma in aerospace engineering of TU Delft in your whole life, unless you do the whole program again. If you lose it, you will never get a replacement. If you spill beer on it during the drinks later today, you will not get a new diploma. The only thing you will be able to get later is a statement of TU Delft that we have given you a diploma, but we're never going to give you a copy of that. So guard it with your life. That said, thank you very much. We're going to close the session.